Quantum mechanics, often referred to as the most successful theory of the microscopic world, challenges our traditional views of the universe. It's a realm where the rules we apply to our everyday experiences no longer seem to hold, and strange, counterintuitive phenomena emerge. Among these phenomena is the Heisenberg Uncertainty Principle, which stands as one of the most perplexing concepts in all of physics. But before diving into the intricacies of this principle, we must first understand the foundations of quantum mechanics and its revolutionary departure from classical physics. At the turn of the 20th century, scientists were beginning to encounter phenomena that couldn't be explained by classical physics. Classical mechanics, pioneered by Isaac Newton, was built on the assumption that the universe operated in a deterministic fashion. If you knew the initial conditions of a system, such as the position and velocity of a particle, you could predict its future behavior with perfect accuracy. However, experiments, particularly those involving light and atomic behavior, began to reveal inconsistencies. Classical theory couldn't account for these results, and this prompted the development of quantum theory. Quantum mechanics arose from a series of groundbreaking discoveries, beginning with Max Planck's work on blackbody radiation in 1900. Planck proposed that energy is quantized and can only exist in discrete units, or quanta. This idea was revolutionary because it went against the long-held belief that energy could be continuously divided. Planck's discovery paved the way for Albert Einstein's explanation of the photoelectric effect in 1905, where he proposed that light itself is quantized, behaving as particles called photons. These ideas, along with others from physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, eventually culminated in the development of quantum mechanics, a theory that fundamentally redefined how we think about matter, energy, and the universe. The key departure that quantum mechanics made from classical physics was the idea that, at microscopic scales, particles, such as electrons, do not follow predictable, deterministic paths. Instead, their behavior is probabilistic, meaning we can only predict the likelihood of finding a particle in a certain place at a certain time. This was a drastic shift from classical ideas, where objects like planets or billiard balls move in predictable trajectories based on the forces acting on them. One of the central tenets of quantum mechanics is wave-particle duality. This principle, proposed by Louis de Broglie in the 1920 seconds, suggests that particles, like electrons, exhibit both wave-like and particle-like properties. This was demonstrated in the famous double-slit experiment, which showed that electrons, when passed through two slits, create an interference pattern characteristic of waves. However, when observed, electrons behaved like particles, landing at specific points. This duality led physicists to develop a new framework for understanding the behavior of matter, one that didn't rely on the concepts of classical physics. It was in this context that Werner Heisenberg, a key figure in the development of quantum theory, introduced his uncertainty principle. In 1927, Heisenberg proposed that there are fundamental limits to how precisely we can measure certain pairs of physical properties of a particle, such as its position and momentum. The more precisely we try to measure one property, the less precisely we can measure the other. This principle was not a result of experimental limitations or faulty equipment. It was inherent in the nature of the quantum world itself. Heisenberg's insight represented a major shift in the way physicists thought about measurement, suggesting that at the quantum level, observation itself affects the system being observed. This principle challenged the assumptions of classical physics, where it was thought that measurement could reveal an objective reality independent of the observer. In classical mechanics, measuring an object's position and velocity simultaneously could, in theory, provide a full description of its state. But Heisenberg's uncertainty principle undermined this, suggesting that at microscopic scales, the very act of measurement changes the system being measured. This realization brought with it the understanding that we cannot fully know a particle's state at any given time, at least not in the way we are accustomed to in the macroscopic world. To better understand this, consider the concept of position and momentum. In classical physics, these two quantities are intimately related. If you know the position of a particle and its velocity, you can calculate its momentum mass times velocity. But in the quantum world, the relationship between position and momentum is not so straightforward. The uncertainty principle tells us that there is a limit to how well we can simultaneously know both of these properties. The more accurately we measure one, say, the position, the less certain we become about the other momentum. In mathematical terms, the uncertainty principle is expressed as delta. Delta is greater than or equal to 4 deltax deltap is greater than or equal to 4 pi h, where deltax, is the uncertainty in position, deltap is the uncertainty in momentum, and h is Planck's constant, a fundamental constant in quantum mechanics. This equation quantifies the uncertainty and provides a precise mathematical relationship between the uncertainty in position and momentum. The principle suggests that there is an inherent fuzziness in the quantum world that makes absolute certainty impossible. This fuzziness is not due to limitations in our measurement tools, but is a fundamental feature of nature itself. At first glance, the idea of uncertainty may seem counterintuitive, especially given our everyday experiences where we can measure the experience, position, and velocity of macroscopic objects with great precision. If you track a car on the highway, for example, you can measure its position and speed with a high degree of accuracy. But quantum particles, such as electrons, behave very differently. Their positions and velocities are not well defined in the way we might expect from classical objects. Instead, they are described by probabilities, with their position and momentum existing as a range of possible values until measured. This behavior was a revelation and a departure from everything that classical physics had taught us about the deterministic nature of the universe. The uncertainty principle also ties into the concept of wave-particle duality. Particles like electrons can be thought of as waves, and the act of measuring one property such as position disturbs the wave, making it impossible to know other properties like momentum with perfect certainty. The wave function, which describes the probability distribution of a particle's properties, can only give us a range of possibilities. When we measure a particle, we collapse the wave function to a single value, but the uncertainty remains in the system. This idea of uncertainty extends beyond just position and momentum. The principle has broader implications for the limits of knowledge in quantum mechanics. It tells us that there are fundamental limits to what we can know about a quantum system. This concept runs counter to the philosophy of classical mechanics, where it was assumed that the universe was fully knowable given enough information. In the quantum world, the very fabric of reality is probabilistic and uncertain, suggesting that there are limits to human knowledge and understanding. The uncertainty principle also has profound philosophical implications. If we cannot know the position and momentum of a particle with perfect certainty, what does that say about the nature of reality itself? Does this uncertainty mean that the universe is inherently indeterministic, or does it simply reflect the limits of our measurement capabilities? These questions have sparked debates not only among physicists but also among philosophers who grapple with the implications of Heisenberg's principle for our understanding of the universe. The uncertainty principle challenges our classical notions of objectivity and suggests that at the deepest level of reality, things are not as clear-cut as they seem. In the next part of this exploration, we will delve deeper into the consequences of the uncertainty principle, including how it influences our understanding of the quantum world and its applications in modern technology. We will also examine the philosophical debates it has sparked as well as its implications for the nature of reality and the limits of human knowledge. But before we go further, it is essential to recognize the profound impact that the Heisenberg Uncertainty Principle has had on our scientific worldview and the way we perceive the universe. The Heisenberg Uncertainty Principle, with its profound implications for the world of quantum mechanics, has led to a radical shift in our understanding of the universe. After Heisenberg's initial formulation in 1927, the concept gradually became one of the cornerstones of quantum theory, deeply influencing both the direction of scientific inquiry and philosophical debates. While the uncertainty principle may have seemed perplexing to many when it was first proposed, its influence on science and technology over the following decades cannot be overstated. Understanding how this principle works, its impact on physics, and its broader implications is essential for comprehending the quantum world. The uncertainty principle's most direct implication is the concept of quantum indeterminacy, meaning that particles at the quantum level do not have a single, well-defined state until they are observed. Unlike classical objects, which are assumed to have definite positions and velocities regardless of whether we observe them, quantum particles exist in a superposition of possibilities, represented by a wave function. When we measure a particle's position, we collapse its wave function, forcing it into one definite state. However, this act of observation introduces a fundamental uncertainty in the particle's momentum and vice versa. This idea stands in stark contrast to classical physics, where objects like planets or cars move along predictable paths that can be mathematically described and calculated. Classical physics assumes that if we know the current state of an object, its position, velocity, and other properties, we can predict where it will be in the future. The determinism of classical mechanics, rooted in Newtonian physics, suggested that, with perfect knowledge, the future was completely predictable. However, Heisenberg's principle introduced a new kind of probabilistic thinking to physics, the idea that, at the quantum level, the future of particles is governed by probabilities, not certainties. The principle also plays a crucial role in wave-particle duality, one of the most puzzling aspects of quantum mechanics. The duality principle asserts that particles, such as electrons and photons, can behave both like particles and like waves. This was first demonstrated by the double-slit experiment, where particles passing through two slits create an interference pattern, something that is characteristic of waves, not particles. However, when we try to measure the particle's position, its wave-like behavior disappears, and it behaves like a particle. Heisenberg's uncertainty principle helps explain this duality. It suggests that when we measure a particle's position, we disturb its wave function, which means we can no longer know its momentum precisely. This disruption is a direct consequence of the uncertainty principle. Another profound consequence of Heisenberg's principle is its implications for quantum measurement and the act of observation. In the quantum world, measurement is not a passive process. Instead, the act of measuring a property of a particle changes the particle itself. This is fundamentally different from classical measurement, where the observer is assumed to be separate from the system being measured. In quantum mechanics, however, the observer cannot be decoupled from the system. The uncertainty principle reveals that the act of measurement introduces uncertainty, affecting the very system being studied. This leads to what is known as quantum non-locality, a concept that states particles can influence one another instantaneously, even over vast distances, in ways that seem to defy classical ideas of space and time. The uncertainty principle has important consequences for understanding the limits of knowledge in quantum mechanics. In classical physics, it was assumed that, in principle, any physical system could be described with complete precision, given enough information. This was in line with the notion of determinism, where the state of the system at any time completely determined its future behavior. However, in quantum mechanics, Heisenberg's principle tells us that there are intrinsic limits to what we can know about a system. No matter how precise our instruments become, there will always be a fundamental level of uncertainty that cannot be eliminated. This realization has significant implications for the way we approach scientific inquiry. The uncertainty principle has also led to the development of new ideas about the nature of reality itself. According to some interpretations of quantum mechanics, the world at its most fundamental level is not deterministic but probabilistic. Instead of existing in a definite state, particles only choose a position or momentum when we measure them. This idea challenges the classical view of a stable, predictable universe, suggesting that uncertainty and randomness are inherent in the very fabric of reality. These interpretations have spurred debates about the philosophical implications of quantum mechanics, with some physicists and philosophers arguing that the universe is not as solid and real as it appears to be at larger scales. Another area where the uncertainty principle plays a crucial role is in quantum tunneling. This phenomenon occurs when particles pass through potential barriers that they classically should not be able to surmount. According to classical mechanics, if a particle doesn't have enough energy to overcome a barrier, it cannot pass through it. However, in the quantum world, particles sometimes tunnel through barriers even when they don't have the classical energy to do so. The uncertainty principle helps explain this effect by suggesting that there is always some uncertainty in the energy and position of a particle, allowing it to pass through barriers under certain conditions. Quantum tunneling is a key concept in many physical phenomena, including nuclear fusion and the operation of semiconductors in modern electronics. Beyond theoretical physics, the uncertainty principle has had a transformative impact on modern technology. Quantum mechanics, including the uncertainty principle, has led to the development of technologies that are revolutionizing our world. Quantum computers, for instance, exploit the probabilistic nature of quantum mechanics to solve problems that are currently beyond the reach of classical computers. Quantum cryptography, another technology inspired by quantum theory, takes advantage of the uncertainty principle to create unbreakable codes for secure communication. By using the principle that measurement disturbs a quantum system, quantum cryptography ensures that any attempt to intercept a quantum key will disturb the system, alerting the user to the presence of eavesdroppers. While the uncertainty principle may seem abstract and disconnected from our everyday lives, its consequences are far-reaching and far more practical than they may first appear. Technologies that rely on quantum mechanics, such as lasers, MRI machines, and semiconductors, are all possible due to the strange, probabilistic nature of particles at the quantum level. These advancements highlight the importance of understanding the underlying principles of quantum mechanics, even if they seem unintuitive or abstract at first. Heisenberg's uncertainty principle is not just a statement about the limits of measurement. It is a reflection of the very nature of the quantum world. It forces us to confront the idea that certainty, so central to classical physics and human understanding, does not apply at the quantum level. Instead, we must embrace a world where uncertainty is intrinsic to the fabric of reality, and where observation plays a key role in shaping the very world we seek to understand. The implications of this principle extend far beyond the realm of physics, challenging our deepest assumptions about the universe, the nature of knowledge, and the role of the observer in shaping reality. Ultimately, the Heisenberg Uncertainty Principle not only reshaped our understanding of the quantum world, but also transformed the way we think about the limits of human knowledge and the nature of the universe. By accepting that uncertainty is a fundamental part of the universe, we open ourselves to new ways of thinking, new possibilities for technology, and a deeper appreciation for the mysteries that still await discovery. While the quantum world may be mysterious and often defy our intuitions, it is this very mystery that drives us forward in our quest for knowledge and understanding. Heisenberg's principle is not just a scientific concept. It is a gateway to a new way of thinking about the world around us. The Heisenberg Uncertainty Principle, one of the fundamental tenets of quantum mechanics, fundamentally reshapes how we understand the universe, especially behavior of particles at the microscopic level. It holds that certain pairs of physical properties, such as position and momentum, cannot both be measured with arbitrary precision at the same time. This principle challenges our classical understanding of determinism and introduces a probabilistic nature to quantum systems. Heisenberg's groundbreaking insight has had profound effects not only on the field of physics, but also on the way we perceive the limits of knowledge and observation. Understanding the uncertainty principle begins with appreciating its departure from classical mechanics. In classical physics, the universe was considered to be deterministic. If one knew the initial conditions of a system, like the position and velocity of an object, one could predict its future behavior with perfect accuracy. This ideal aligns with Newtonian mechanics, where the position and momentum of a particle are fully determined by external forces and, in theory, could be known precisely at any given time. However, as the 20th century unfolded, new experimental results, particularly in the fields of optics and atomic structure, began to reveal that the classical worldview was insufficient for explaining phenomena at very small scales. Quantum mechanics arose to account for these anomalies. With the work of Max Planck, Albert Einstein, Niels Bohr, and others, a new understanding of the nature of light, atoms, and particles began to emerge. This understanding diverged sharply from classical mechanics by proposing that particles, like electrons, could no longer be described as simple objects with definite positions and velocities. Instead, quantum particles are better described by a probabilistic wave function, a mathematical function that gives the probability of finding a particle in a given position. This shift from determinism to probability was one of the first major conceptual revolutions in physics. It was against this backdrop that Werner Heisenberg developed his uncertainty principle. In 1927, Heisenberg proposed that there are inherent limits to the precision with which certain pairs of properties, such as position and momentum, can be known. More precisely, the more accurately we measure one property, the less accurately we can measure the other. This principle isn't due to limitations in measurement devices, but is intrinsic to the nature of quantum systems. It reveals that at the quantum level, there is no such thing as absolute precision in measuring these pairs of properties simultaneously. Instead, uncertainty is an essential feature of the quantum world. This insight into the nature of quantum particles led Heisenberg to formulate a mathematical expression for his principle. Delta is greater than or equal to h4 pi, delta x, c dot delta p, gq frax key, 4 pi delta is greater than or equal to 4 pi h, where delta x represents the uncertainty in position, delta p represents the uncertainty in momentum, and hhh is Planck's constant, a fundamental physical constant that defines the scale of quantum effects. This inequality quantifies the relationship between the uncertainty in position and momentum. It suggests that the product of these two uncertainties must be greater than or equal to a certain constant. This equation embodies the core of Heisenberg's uncertainty principle, highlighting the fundamental trade-off between how much we can know about a particle's position and its momentum. One of the key features of the uncertainty principle is that the uncertainty in position and momentum is not a result of flawed measurements or technological limitations. Instead, it is a fundamental aspect of quantum objects. In classical mechanics, it would be possible to simultaneously measure both the position and momentum of a particle with perfect accuracy, given enough precision in the instruments used. But in the quantum world, this is simply not possible. The uncertainty principle tells us that particles such as electrons do not have well-defined positions and momenta at the same time. This is not because we cannot measure them with enough precision. It's because the very nature of quantum particles means that they are not localized in space and do not have well-defined momentum simultaneously. This realization that the act of measurement itself influences the state of the system is one of the most profound shifts in scientific thought. In classical mechanics, measurement was considered passive observers were thought to be independent of the system they observed. But in quantum mechanics, the observer plays a crucial role. By measuring a particle's position, we collapse its wave function, forcing it into a specific state. However, this measurement disturbs the system, making it impossible to simultaneously measure its momentum with complete accuracy. This is one of the central features of quantum mechanics that separates it from classical physics. The uncertainty principle is not just limited to position and momentum. While position and momentum are the most commonly discussed pair of properties in relation to the uncertainty principle, other pairs of properties, such as energy and time, also exhibit similar relationships. For example, the energy of a quantum system and the time over which that energy is measured are also subject to an uncertainty relationship. This further underscores the broader implications of the uncertainty principle, which affects not just the position and momentum of particles, but also other fundamental quantities. Heisenberg's uncertainty principle can also be understood in terms of wave-particle duality. This concept, proposed by Louis de Broglie in the early 20th century, posits that particles, such as electrons, can exhibit both wave-like and particle-like properties. The wave-particle duality of quantum objects is a fundamental feature of quantum mechanics, but it is also what makes the uncertainty principle so significant. When an electron behaves like a wave, its position is spread out across a region of space, making it impossible to pinpoint the exact location of the electron. The more tightly we try to localize the wave, that is to say, by measuring its position more precisely, the less well-defined its momentum becomes, since the wave's spread in space is directly related to its spread in momentum. To further illustrate this concept, consider the example of an electron in an atom. When we attempt to measure its position, we cause its wave function to collapse to a specific location. However, this action inherently increases the uncertainty in the momentum of the electron. This is because, in quantum mechanics, the electron cannot exist as a simple point particle. Rather, it exists as a cloud of probabilities, spread over a range of possible positions and momenta. The uncertainty principle is the mathematical expression of this fundamental fuzziness in the quantum world. The uncertainty principle also has significant implications for the limits of human knowledge. In classical physics, it was assumed that the universe operated according to precise laws that, in theory, could be known completely if we had enough information. This was the basis of determinism. If we knew the exact state of a system, we could predict its future with certainty. However, the uncertainty principle introduces an element of fundamental unpredictability at the quantum level. It tells us that there are inherent limits to what we can know about the universe. We cannot fully predict the behavior of quantum particles because there are intrinsic uncertainties in their state. This shift from determinism to probabilism has far-reaching implications. It challenges the classical worldview, where certainty was the norm, and forces us to reconsider our understanding of reality itself. If the universe is fundamentally uncertain at its most basic level, How can we be certain of anything in the macroscopic world? The uncertainty principle raises deep philosophical questions about the nature of reality and whether it is possible to ever truly know the world as it is. In quantum mechanics, we are forced to accept that the world is not always knowable in the way we might hope, and that uncertainty is an inescapable part of nature. As we explore the consequences of Heisenberg's uncertainty principle, we begin to see its far-reaching impact on both theoretical and experimental physics. The principle has shaped the development of quantum theory and influenced fields ranging from quantum computing to the interpretation of quantum mechanics itself. It has also led to groundbreaking technologies that rely on the principles of quantum mechanics, such as quantum cryptography, which leverages the uncertainty inherent in quantum systems to create secure communication systems. Moreover, Heisenberg's insight has sparked numerous debates in the scientific and philosophical communities. Some argue that the uncertainty principle represents a fundamental aspect of nature, showing that the universe is inherently probabilistic and that exact knowledge of the future is impossible. Others suggest that the principle might be an indication of the limits of our current understanding and that future advances in science may one day allow us to circumvent the uncertainty in quantum systems. These debates continue to shape the way we think about the nature of reality, knowledge, and the universe. The uncertainty principle also informs much of our current understanding of the quantum world. Quantum mechanics, with its probabilistic framework, offers a much richer and more nuanced picture of reality than classical physics ever could. The principle reveals that the universe is not made up of objects with fixed properties, but instead consists of systems that are defined by probabilities. This understanding has led to the development of technologies that harness quantum behavior, such as quantum computers, which promise to revolutionize computing by leveraging the power of quantum states. In conclusion, the Heisenberg Uncertainty Principle challenges our traditional notions of determinism and introduces an element of fundamental unpredictability into the very fabric of nature. It forces us to rethink how we approach measurement, knowledge, and reality itself. As we continue to explore the quantum world, the uncertainty principle remains one of the most profound and perplexing concepts, offering new insights into the behavior of particles and the limits of human understanding. The uncertainty principle, though initially perplexing, has grown to be one of the most important ideas in quantum mechanics. Heisenberg's assertion that we cannot simultaneously know the position and momentum of a quantum particle with absolute precision altered the course of physics and reshaped our understanding of the universe. While the principle was revolutionary in its time, its far-reaching implications stretch across multiple domains of science, technology, and philosophy, pushing the boundaries of human knowledge and our understanding of reality itself. To comprehend the true magnitude of this discovery, it's essential to delve deeper into its consequences, both theoretical and practical, and its philosophical significance. The first critical consequence of the uncertainty principle is that it fundamentally challenges the concept of determinism. Classical physics, grounded in the ideas of Isaac Newton and others, operated under the assumption that if we had complete information about a system, we could predict its future behavior with perfect certainty. If we knew the position and momentum of a particle, its future path could be calculated precisely. In this framework, everything in the universe was deterministic, and the future unfolded according to the precise laws of nature. However, Heisenberg's uncertainty principle introduced a stark departure from this notion. It asserts that, at the quantum level, there is no such thing as complete knowledge of both position and momentum at the same time. The more accurately we measure one of these properties, the less certain we become about the other. This does not stem from limitations in measurement equipment, but from the very nature of quantum objects themselves. Therefore, The idea that the universe's future behavior can be predicted with certainty breaks down in the quantum realm. This realization is one of the most profound consequences of Heisenberg's principle. It implies that, at a fundamental level, the universe operates on probabilistic laws rather than deterministic ones. This probabilistic view of reality represents a profound philosophical shift. It challenges the classical notion that the world is a collection of objects that can be fully understood and predicted if we simply know enough about them. In quantum mechanics, this is no longer the case. Instead of being able to make precise predictions about the future, we must accept that uncertainty and randomness are intrinsic features of nature. The uncertainty principle is a mathematical expression of this randomness, suggesting that certain aspects of reality, position, and momentum cannot be pinned down at the same time. In other words, uncertainty is not just an inconvenience or limitation of measurement. It is a fundamental characteristic of the physical world. Another significant implication of the uncertainty principle is its relationship with the wave-particle duality of quantum objects. One of the most puzzling aspects of quantum mechanics is that particles such as electrons exhibit both wave-like and particle-like behavior, depending on the experimental setup. For example, in the famous double-slit experiment, particles behave like waves when not being observed, forming interference patterns as they pass through two slits. However, when measured, the particles behave like discrete objects, landing at specific locations, just as classical particles would. Heisenberg's uncertainty principle helps explain this behavior. In quantum mechanics, particles are described by wave functions, mathematical descriptions of the probability of finding a particle in a particular place at a given time. The more we try to localize a particle, that is to say, measure its position more precisely, the less well-defined its momentum becomes. The wave-like nature of quantum particles means that their position is not fixed, and trying to measure it with great precision collapses their wave function, resulting in an inherent uncertainty in their momentum. This phenomenon of wave-particle duality and the associated uncertainty is another radical departure from classical physics, where particles were thought to behave in a predictable, deterministic manner. The uncertainty principle reveals that, at the quantum level, particles do not have definite positions or momenta until they are measured. Instead, they exist in a superposition of possible states, only deciding on a particular position or momentum upon observation. This realization not only challenged our classical ideas of particles, but also reshaped the entire framework of physics, demanding a probabilistic approach to understanding the fundamental workings of nature. One of the more intriguing consequences of the uncertainty principle is its relationship with the nature of observation itself. In classical mechanics, measurement was a passive process. It was assumed that the act of measurement did not influence the system being measured. In quantum mechanics, however, the very act of observing a quantum system disturbs it. For instance, when we measure the position of a particle, its wave function collapses, and the particle takes on a definite position. But this process also introduces uncertainty into its momentum, as per Heisenberg's principle. This observation-disturbance relationship is a key aspect of quantum mechanics and illustrates how the act of measurement in the quantum world is not as simple as it is in classical physics. This interaction between the observer and the system leads to what is called the observer effect. The observer effect is a fundamental feature of quantum mechanics that suggests the outcome of an experiment can be altered by the act of observation itself. This is starkly different from classical physics, where the observer is considered external to the system and their measurements do not affect the system. In quantum mechanics, however, the observer is an active participant in the unfolding of the system's behavior. The uncertainty principle, therefore, underscores the fact that knowledge of the quantum world is inherently limited, not because of technological constraints, but because the very nature of quantum systems involves an interplay between the system and the observer. The philosophical implications of the uncertainty principle are profound. It suggests that the universe at its most fundamental level is not deterministic or predictable, but probabilistic and uncertain. This realization has led to various interpretations of quantum mechanics, each grappling with the meaning of uncertainty and the role of the observer. One of the most famous interpretations is the Copenhagen interpretation, which posits that particles do not have definite properties until they are observed. According to this view, the act of observation causes the collapse of the wave function, giving the particle a definite state. Other interpretations, such as the many worlds interpretation, take a different approach. The many worlds interpretation suggests that all possible outcomes of a quantum measurement actually occur in separate, non-communicating branches of the universe. In this view, the universe is constantly splitting into multiple realities, each corresponding to a different outcome of a quantum event. This interpretation challenges our traditional notions of reality and observation, suggesting that the universe is far more complex than we can intuitively grasp. Another significant consequence of the uncertainty principle is its influence on the development of modern technologies. While the principle suggests that we cannot know certain properties of quantum particles with absolute certainty, it also provides the foundation for technologies that exploit these quantum effects. One of the most notable applications of quantum mechanics is quantum computing, which seeks to leverage the probabilistic nature of quantum particles to perform computations far beyond the capabilities of classical computers. Quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to superposition. This allows quantum computers to perform certain calculations exponentially faster than classical computers. Similarly, quantum cryptography takes advantage of the uncertainty principle to create secure communication channels. In quantum cryptography, the act of measuring a quantum key disrupts its state, alerting the parties involved to the presence of an eavesdropper. This makes quantum cryptography theoretically immune to hacking, as any attempt to intercept the quantum key would disturb the system and make the intrusion detectable. The uncertainty principle is also crucial in the field of quantum tunneling, a phenomenon where particles can pass through energy barriers that they classically should not be able to surmount. Quantum tunneling has numerous applications, including in the design of semiconductor devices and nuclear fusion. The principle's probabilistic nature allows particles to tunnel through barriers, enabling the development of technologies that rely on this quantum effect. Despite its theoretical and technological importance, the uncertainty principle also serves as a reminder of the limits of human knowledge. It challenges the classical notion that if we gather enough information about a system, we can fully understand and predict its behavior. The uncertainty principle suggests that there are inherent limitations to what we can know about the quantum world. As such, it forces us to confront the fact that there may be aspects of reality that are forever beyond our grasp. In conclusion, Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, reshaping our understanding of the universe at its most fundamental level. It introduces a probabilistic view of reality, where uncertainty is not just a limitation of our instruments, but a fundamental feature of nature. The uncertainty principle challenges classical determinism, alters our conception of observation, and leads to groundbreaking technological advancements. It also opens up philosophical questions about the nature of reality, knowledge, and the role of the observer. Despite the profound uncertainty it reveals, the principle has brought us closer to understanding the deepest mysteries of the universe. The Heisenberg Uncertainty Principle, a foundational concept in quantum mechanics, has been a crucial pivot in the way we understand the natural world. Werner Heisenberg's insight into the intrinsic limitations of measurement at the quantum level fundamentally transformed our understanding of reality. This principle is often seen as one of the most profound and perplexing elements of quantum theory, challenging the deterministic framework of classical physics and introducing a probabilistic view of the universe at its smallest scales. Understanding the deeper ramifications of the uncertainty principle requires an exploration of its core tenets and the way it shaped modern physics, technological advancements, and philosophical debates about the nature of reality itself. At the heart of the uncertainty principle is the idea that certain pairs of physical properties, such as a particle's position and momentum, cannot be measured with infinite precision simultaneously. The more accurately we measure one of these properties, the less precisely we can measure the other. This relationship, expressed mathematically by Heisenberg's inequality, deltax deltap is greater than or equal to h4 pi delta xc dot delta p gq frax h4 pi deltax deltap is greater than or equal to 4 pi h, where deltax delta x deltax is the uncertainty in position, deltap delta p deltap is the uncertainty in momentum, and hhh is Planck's constant, underscores the fundamental limits of knowledge in the quantum world. Unlike classical mechanics, where one could assume that both position and momentum are knowable with precision, quantum mechanics reveals that at the microscopic scale, the act of measurement itself disturbs the system, making it impossible to determine both properties simultaneously with perfect accuracy. This principle shattered classical ideas about a deterministic universe and forced physicists to embrace the inherent probabilistic nature of quantum systems. The uncertainty principle's challenge to classical mechanics lies not only in its assertion of limited knowledge, but also in its departure from the classical worldview that governed the universe for centuries. In classical physics, objects were treated as having well-defined positions, velocities, and trajectories at all times, with the assumption that the universe was inherently predictable. If you knew the initial state of a system, its position, velocity, and other properties, you could predict its future state with perfect certainty. This ideal of a fully deterministic universe was championed by Newtonian mechanics, and it underpinned much of the scientific and philosophical thinking of the 17th through 19th centuries. However, quantum mechanics, with Heisenberg's principle as one of its cornerstones, challenged this worldview, introducing a probabilistic approach to understanding the behavior of particles and systems at the microscopic level. The Heisenberg Uncertainty Principle fundamentally reshaped our perception of measurement in science. In classical physics, measurement was assumed to be a passive act. The observer did not alter the system being measured. If a person were to measure the position and momentum of an object, they could do so without changing the state of the system. However, in quantum mechanics, the situation is vastly different. The act of measurement in quantum systems is inherently active. Measuring one property of a quantum particle inevitably disturbs the system, which is why the uncertainty principle arises. When we measure a particle's position with greater accuracy, its momentum becomes more uncertain, and vice versa. This uncertainty is not a consequence of technological limitations or experimental errors, but a fundamental feature of the quantum world. This principle highlights a profound shift in our philosophical understanding of reality. The uncertainty principle suggests that at the quantum level, the universe is not composed of discrete objects with definite properties, as classical mechanics suggested, but rather a system of probabilities. Quantum objects, such as electrons or photons, are better described by wave functions, mathematical functions that encapsulate the probability of finding a particle in a given state or location. These wave functions describe a range of possible outcomes rather than a single, definite outcome. When a measurement is made, the wave function collapses, and the particle assumes a definite state, but the process of measurement introduces an inherent uncertainty in the complementary property, such as momentum or position. This probabilistic nature of quantum mechanics was a stark departure from the deterministic views of classical physics and led to the development of new interpretations of reality. In classical mechanics, the future of a system is fully determined by its current state. For example, if we know the position and velocity of a ball rolling down a hill, we can predict exactly where it will be at any given time in the future. In quantum mechanics, however, due to the uncertainty principle, we cannot make precise predictions about a particle's future trajectory. Instead, we can only calculate the probability of finding a particle in a certain place or state. This shift from a deterministic to a probabilistic view of the universe has profound implications for the way we understand everything from the behavior of subatomic particles to the very nature of reality. The uncertainty principle is also closely related to the concept of wave-particle duality, one of the defining features of quantum mechanics. Wave-particle duality refers to the phenomenon where particles, such as electrons and photons, exhibit both wave-like and particle-like behavior depending on the experimental conditions. This duality was first demonstrated by the double-slit experiment, in which particles of light or matter passed through two slits and created an interference pattern, characteristic of waves, on a screen behind the slits. However, when the particles were observed, they behaved as discrete particles, landing on the screen at specific points rather than forming a continuous wave pattern. The uncertainty principle helps explain this wave-particle duality. When particles like electrons behave as waves, their position is spread out over space, meaning they do not have a definite position until they are observed. When an attempt is made to measure the position of the particle with great precision, the uncertainty in its momentum increases, and the wave-like behavior collapses, causing the particle to behave like a discrete object. This collapse of the wave function is a direct result of Heisenberg's uncertainty principle, which states that precise knowledge of one property, such as position, disturbs the system and makes it impossible to know the complementary property momentum simultaneously with accuracy. The consequences of the uncertainty principle extend far beyond theoretical physics, influencing the development of technologies that have become essential in modern life. One of the most significant applications of quantum mechanics and the uncertainty principle is in the field of quantum computing. Unlike classical computers, which process information as binary digits, 0 seconds and 1 second, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to the superposition principle. This ability to exist in multiple states allows quantum computers to solve certain problems much more efficiently than classical computers. The probabilistic nature of quantum mechanics, as encapsulated by the uncertainty principle, plays a crucial role in the development of quantum computing, as qubits rely on the behavior of quantum particles, which are governed by these principles. Similarly, the uncertainty principle has found applications in quantum cryptography. Quantum key distribution, a method for secure communication, uses the principles of quantum mechanics to detect any eavesdropping. If a quantum key is measured by an unauthorized observer, the uncertainty principle guarantees that the act of measurement will disturb the quantum system, alerting the legitimate parties to the presence of the eavesdropper. This feature makes quantum cryptography theoretically immune to hacking, as any attempt to intercept the transmission will be detectable due to the disturbance it causes to the quantum state. The uncertainty principle also underpins the phenomenon of quantum tunneling, which occurs when particles pass through energy barriers that they classically should not be able to surmount. This effect is crucial in processes such as nuclear fusion and has applications in semiconductor technology. quantum tunneling is a direct result of the probabilistic nature of quantum systems, and Heisenberg's uncertainty principle plays a central role in explaining why particles can tunnel through energy barriers that would otherwise be impenetrable. Beyond its applications, the uncertainty principle continues to raise philosophical questions about the nature of reality and the limits of human knowledge. If the universe at its most fundamental level is probabilistic rather than deterministic, then the classical idea of an objective reality that exists independently of our perception is called into question. The act of measurement, which in quantum mechanics plays a crucial role in determining the state of a system, suggests that reality is not a passive, objective entity, but one that is shaped by the observer's interaction with it. This idea has sparked intense debates about the nature of consciousness and its relationship to the physical world. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality does not exist in a definite state until it is observed. According to this view, the wave function representing a particle's state encompasses all possible outcomes, and the act of measurement forces the system to collapse into one of those possible outcomes. Other interpretations, such as the many worlds interpretation, propose that all possible outcomes of a quantum measurement actually occur in separate, parallel realities, each corresponding to a different outcome. These philosophical questions continue to fuel ongoing debates about the implications of quantum mechanics for our understanding of the universe. The uncertainty principle also emphasizes the limits of human knowledge. In classical physics, it was assumed that if we could gather enough information about a system, we could fully understand and predict its behavior. But the uncertainty principle tells us that no matter how much information we gather, there will always be fundamental limits to our knowledge about certain properties of quantum systems. This realization has profound implications for how we think about the relationship between knowledge, observation, and reality. It suggests that the quest for complete knowledge of the universe may be inherently limited, and that some aspects of reality may forever remain beyond our understanding. In conclusion, the Heisenberg Uncertainty Principle is a cornerstone of quantum mechanics, challenging classical ideas of determinism, measurement, and knowledge. It reveals the probabilistic nature of the quantum world, where the precise knowledge of one property of a particle necessarily leads to uncertainty in another. The principle has had profound implications not only for theoretical physics but also for the development of groundbreaking technologies such as quantum computing and quantum cryptography. It has also raised deep philosophical questions about the nature of reality and the limits of human knowledge. Despite its abstract nature, the uncertainty principle continues to shape our understanding of the universe and drive the quest for knowledge, offering new insights into the mysteries of the quantum world. The Heisenberg Uncertainty Principle stands as one of the pillars of quantum mechanics, reshaping our understanding of the microscopic world and fundamentally altering the way we think about the universe. Its implications reach far beyond the realm of theoretical physics, influencing our views on determinism, the nature of reality, and the limits of human knowledge. To fully appreciate the scope of this principle and its profound effects, it is important to explore its consequences in more detail, focusing on the principles of wave-particle duality, the philosophical implications of quantum mechanics, and the practical applications that have emerged from these ideas. One of the most significant consequences of the uncertainty principle is its relationship with wave-particle duality, a cornerstone of quantum theory. Wave-particle duality refers to the concept that particles, such as electrons and photons, exhibit both wave-like and particle-like behavior depending on how they are observed. This duality was first demonstrated in experiments like the double-slit experiment, where particles such as light or electrons passed through two slits and formed an interference pattern, a phenomenon characteristic of waves. However, when observed, these particles behaved like discrete objects, showing particle-like behavior. This realization was groundbreaking because it challenged the classical view of particles as distinct, localized objects with well-defined properties, such as position and velocity. The uncertainty principle offers a way to understand this strange behavior. According to Heisenberg, particles like electrons do not have well-defined positions and momenta simultaneously. Their position and momentum exist as ranges of probabilities until they are measured. When an attempt is made to measure a particle's position, its wave function collapses and it assumes a definite position, but this act of measurement introduces uncertainty in its momentum. Similarly, if we measure a particle's momentum precisely, the uncertainty in its position increases. This trade-off between position and momentum is a direct consequence of the uncertainty principle and helps explain the wave-particle duality of quantum particles. This trade-off between position and momentum highlights one of the key departures from classical physics. In classical mechanics, objects were treated as discrete entities with definite positions and velocities. The more accurately we measured these quantities, the better we understood the object's state and could predict its future behavior. However, in the quantum world, the act of measurement itself disturbs the system, and the properties of quantum particles are inherently uncertain. The probabilistic nature of quantum mechanics, as embodied by the uncertainty principle, suggests that particles are not localized in the way classical objects are. Instead, they exist in a superposition of possible states, only choosing a specific state when observed. The implications of this shift from determinism to probability are profound. In classical physics, the future behavior of a system is entirely predictable if we know its initial conditions. The universe unfolds like a giant clockwork mechanism, governed by fixed laws that apply universally. In quantum mechanics, however, uncertainty and probability replace certainty and determinism. The uncertainty principle tells us that even with complete knowledge of a particle's current state, we cannot predict its future position and momentum with certainty. Instead, we can only calculate the probability of finding the particle in a particular location or with a particular momentum. This realization challenges the classical view of a deterministic universe and opens the door to a new, probabilistic understanding of nature. The probabilistic nature of quantum mechanics has led to a re-evaluation of the nature of reality itself. If particles do not have definite properties until they are observed, what does this mean for our understanding of the universe? According to some interpretations of quantum mechanics, such as the Copenhagen interpretation, reality does not exist in a definite state until it is measured. The act of observation collapses the wave function, forcing the particle into a specific state. Before measurement, the particle exists in a superposition of possibilities, each with a certain probability of being realized. This idea implies that reality is not a passive, objective entity, but is actively shaped by the observer. The uncertainty principle, with its focus on the limits of measurement and the role of the observer, plays a central role in this interpretation of quantum mechanics. Other interpretations, such as the many worlds interpretation, offer a different view. According to this interpretation, all possible outcomes of a quantum measurement actually occur, each in a separate, non-communicating branch of the universe. In this view, the uncertainty principle does not imply that reality is shaped by the observer, but rather that the universe continuously splits into multiple parallel realities, each corresponding to a different measurement outcome. While this interpretation is still debated among physicists, it represents a radically different way of understanding the role of observation in quantum mechanics. Regardless of which interpretation is correct, the uncertainty principle forces us to confront the idea that the universe at its most fundamental level is not deterministic but probabilistic, with reality emerging from a web of possibilities rather than a single, fixed outcome. The philosophical implications of the uncertainty principle extend beyond quantum mechanics itself and into broader discussions of knowledge, reality, and the limits of human understanding. For centuries, Western philosophy has been dominated by the idea that knowledge is ultimately attainable through reason and observation. The classical worldview, based on the principles of determinism and objectivity, supported this belief, suggesting that if we could gather enough information about the world, we could fully understand it. However, the uncertainty principle suggests that this ideal of complete knowledge is impossible, at least at the quantum level. No matter how much we know about a quantum system, there will always be inherent uncertainty in its state. This realization has led to a reevaluation of the nature of scientific knowledge. In classical physics, scientists believed that by understanding the underlying laws of nature, they could predict the future behavior of systems with complete accuracy. However, quantum mechanics tells us that there are inherent limits to what we can know. The uncertainty principle is a manifestation of these limits, suggesting that some aspects of the universe are fundamentally unknowable. This realization challenges the idea of an objective, knowable reality and forces us to confront the limits of our ability to understand the world. Despite these philosophical challenges, the uncertainty principle has led to some of the most exciting and practical advancements in modern science and technology. One of the most significant applications of quantum mechanics, and by extension the uncertainty principle, is in the development of quantum computing. Quantum computers leverage the strange properties of quantum particles, such as superposition and entanglement, to perform calculations that are impossible for classical computers. Quantum bits, or qubits, can exist in multiple states simultaneously, allowing quantum computers to process vast amounts of information in parallel. This ability to exploit quantum uncertainty is what gives quantum computers their power, enabling them to solve problems that are currently beyond the reach of classical machines. Similarly, the uncertainty principle has played a crucial role in the development of quantum cryptography. Quantum cryptography uses the principles of quantum mechanics to create secure communication systems that are immune to eavesdropping. In quantum key distribution, for example, the uncertainty principle guarantees that any attempt to intercept a quantum key will disturb the system, alerting the sender and receiver to the presence of an eavesdropper. This application of the uncertainty principle ensures that the transmission of sensitive information can be made secure, even in the face of powerful adversaries. The uncertainty principle also plays a key role in the phenomenon of quantum tunneling, which occurs when particles pass through energy barriers that they classically should not be able to surmount. Quantum tunneling is responsible for many important processes, such as nuclear fusion in stars and the operation of modern semiconductor devices. In these cases, the uncertainty principle allows particles to tunnel through barriers by exploiting the probabilistic nature of quantum systems, offering insights into phenomena that classical physics cannot explain. The uncertainty principle has far-reaching implications that extend well beyond the confines of quantum mechanics. It challenges classical ideas of determinism, measurement, and objectivity, and introduces a new, probabilistic view of the universe. While the principle may seem abstract and counterintuitive, it has proven to be one of the most important and practical ideas in modern science, leading to advances in quantum computing, cryptography, and other fields. It has also sparked deep philosophical debates about the nature of reality, the limits of human knowledge, and the role of the observer in shaping the universe. In the end, the uncertainty principle offers a glimpse into the deeper mysteries of the quantum world, one that continues to captivate scientists and philosophers alike as they strive to unravel the true nature of the universe. In conclusion, the Heisenberg Uncertainty Principle is far more than a mere theoretical concept. It challenges classical physics, reshapes our understanding of measurement and reality, and offers a new framework for interpreting the universe at its most fundamental level. While it brings with it a sense of uncertainty and indeterminacy, it also opens up new realms of scientific discovery and technological innovation. By embracing uncertainty, we are forced to confront the limits of our knowledge and the inherent probabilistic nature of the universe, leading to deeper insights into the mysteries of the quantum world. The Heisenberg Uncertainty Principle is a cornerstone of quantum mechanics, forever changing our understanding of the universe. Its most profound implication is that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with perfect accuracy. This concept goes beyond a mere limitation of measurement tools. It speaks to a fundamental feature of nature itself. The uncertainty is intrinsic to quantum systems, revealing that particles at the microscopic level do not possess well-defined positions and momenta at the same time. This challenges the classical worldview, which assumed that all properties of an object could be precisely known, and instead suggests that reality at its most basic level is inherently probabilistic. This shift from classical physics to quantum mechanics marks a significant departure in how we view the world. Classical mechanics, as developed by Newton and others, was built on the idea that with enough information, we could predict the future behavior of any system. If we knew the exact position and velocity of an object, we could calculate its future trajectory with precision. This determinism formed the foundation of classical science and philosophy. However, the uncertainty principle shattered this ideal by introducing an element of unpredictability and probability at the microscopic level. The more precisely we measure one property of a particle, like its position, the less precisely we can know another, such as its momentum. This is not due to any flaw in our tools or methods. It is a fundamental aspect of quantum particles. At the core of this principle is the idea of wave-particle duality. Quantum objects, like electrons and photons, exhibit both wave-like and particle-like behaviors, depending on how they are observed. This duality had long puzzled scientists, as particles were traditionally understood as solid, localized objects, while waves were spread out over space. In experiments such as the double-slit experiment, quantum particles behaved as waves, creating interference patterns on a screen. But when observed, the particles acted like discrete objects. The uncertainty principle helps explain this phenomenon by suggesting that particles do not have definite positions until they are measured. Before measurement, the particle exists as a probability wave, and attempting to pin down one property, such as position, disturbs the wave and increases the uncertainty of its momentum. Another key concept associated with the uncertainty principle is the observer effect. In classical physics, measurement was assumed to be a passive process. The observer was external to the system, and measuring an object's position or velocity did not influence its state. However, in quantum mechanics, the act of measurement plays an active role. When we observe a particle, we interact with it, and this interaction disturbs its state. For instance, measuring a particle's position forces its wave function to collapse to a specific location, but this action inherently alters its momentum, introducing uncertainty. This observer effect leads to the realization that at the quantum level, the act of observation fundamentally changes the system being observed, making it impossible to separate the two. The philosophical implications of the uncertainty principle are just as profound as its scientific ones. The classical view of the universe held that it was an objective, deterministic system where everything could, in theory, be known if we had enough information. The uncertainty principle challenges this view by introducing intrinsic uncertainty into the fabric of reality itself. If we cannot know both the position and momentum of a particle with absolute certainty, then does that mean the universe is, at its core, indeterministic? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality itself does not exist in a definite state until it is observed. This means that the universe is not a passive object waiting to be discovered, but is instead a system shaped by the observer. This view raises fundamental questions about the nature of reality and the role of consciousness in shaping the world around us. In summary, the Heisenberg Uncertainty Principle is far more than a simple scientific concept. It is a radical shift in how we perceive the nature of the universe. By introducing the idea that uncertainty is an inherent property of quantum systems, it challenges the deterministic worldview of classical physics and opens the door to a probabilistic understanding of reality. The uncertainty principle, along with wave-particle duality and the observer effect, forces us to rethink the very nature of measurement, knowledge, and reality itself. It remains one of the most profound and transformative ideas in modern science, influencing not only quantum physics but also fields as diverse as technology, philosophy, and our understanding of the universe at large. The Heisenberg Uncertainty Principle is a fundamental concept in quantum mechanics that challenges our classical understanding of the physical world. It states that there are inherent limitations to how precisely we can measure certain pairs of properties, such as the position and momentum of a particle, simultaneously. The more precisely one property is measured, the less precisely the other can be known. This is not a result of limitations in measurement tools or techniques, but is an intrinsic feature of quantum systems. The principle fundamentally alters our perception of reality, suggesting that uncertainty is a natural characteristic of the quantum world, rather than a flaw in our instruments. At the heart of this principle is the idea that particles at the quantum level do not have well-defined, simultaneous values for properties like position and momentum. In classical mechanics, it was assumed that objects, such as a ball or planet, could be described with precise values for their position and momentum at any given time. This determinism formed the basis of classical physics. If we knew the initial conditions of a system, we could predict its future behavior with perfect accuracy. However, quantum mechanics reveals a different reality, where the state of a particle is defined by probabilities rather than certainties. The uncertainty principle embodies this shift, demonstrating that our ability to predict the future behavior of particles is constrained by the inherent uncertainties in their properties. This shift is related to the concept of wave-particle duality, which is central to quantum theory. Quantum objects, such as electrons, exhibit both wave-like and particle-like behaviors depending on how they are observed. When quantum particles are not being measured, they are described by a wave function, which represents a probability distribution of where the particle could be found. However, when a measurement is made, such as determining the position of an electron, the wave function collapses, and the particle assumes a definite state. The uncertainty principle comes into play here because measuring one property like position disturbs the wave function, increasing the uncertainty in the particle's momentum. This disturbance of the quantum state during measurement is a direct consequence of the uncertainty principle and helps to explain wave-particle duality. The act of measurement forces a quantum system into a specific state, which means that we can never measure the position and momentum of a particle with perfect accuracy at the same time. Another important consequence of the uncertainty principle is its relationship to the concept of the observer effect in quantum mechanics. In classical physics, measurement was regarded as a passive process. The observer's actions were not thought to influence the system being measured. However, in quantum mechanics, the act of observation itself plays an active role. Measuring a particle's position, for instance, collapses the particle's wave function and forces it into a specific position, but in doing so, it disturbs the system, making it impossible to know the particle's momentum with complete certainty. This active role of the observer in determining the state of a quantum system marks a departure from classical physics, where the observer was an external, uninfluencing entity. The observer effect has profound philosophical implications, suggesting that reality at the quantum level is not fixed or objective, but is influenced by the act of measurement itself. The uncertainty principle also leads to the realization that the universe, at its most fundamental level, is probabilistic rather than deterministic. This departure from the classical view of a predictable, clockwork universe represents one of the most profound shifts in the history of science. In classical mechanics, if we knew the initial conditions of a system, such as the position and velocity of a planet, we could predict its future state with absolute certainty. The universe seemed like a machine, governed by fixed laws that could be fully understood and predicted. However, the Heisenberg Uncertainty Principle reveals that at the quantum level, nature operates according to probabilities. Instead of knowing exactly where a particle is, or what its momentum is, we can only calculate the probability of finding a particle in a given location or with a specific momentum. This probabilistic view has far-reaching consequences, not just for physics, but for our broader understanding of reality. It suggests that there are limits to what we can know, and that the universe is not as predictable or knowable as we once thought. In practical terms, the uncertainty principle has had significant implications for the development of quantum technologies. One of the most notable examples is quantum computing, which relies on the principles of superposition and entanglement to perform calculations. Quantum computers process information using quantum bits, or qubits, which can exist in multiple states at once, thanks to the superposition principle. The uncertainty principle plays a role in this by emphasizing the probabilistic nature of quantum states, allowing quantum computers to solve certain problems much faster than classical computers. Another important application of the uncertainty principle is in quantum cryptography. Quantum key distribution, which is used to create secure communication systems, exploits the inherent uncertainties in quantum systems. If a quantum key is intercepted or measured by an unauthorized party, the uncertainty principle ensures that the system will be disturbed, alerting the sender and receiver to the intrusion. This ability to detect eavesdropping based on the disturbance of the system is one of the key advantages of quantum cryptography. In conclusion, the Heisenberg Uncertainty Principle is not just a theoretical concept, but a fundamental aspect of the quantum world with far-reaching implications. It challenges classical ideas of determinism and measurement, introducing a probabilistic and dynamic understanding of reality. The principle's relationship to wave-particle duality, the observer effect, and quantum technologies underscores its profound influence on both theoretical and applied physics. As we continue to explore the quantum world, the uncertainty principle will remain a crucial tool for understanding the strange and often counterintuitive behaviors of particles at the smallest scales. The principle forces us to reconsider the nature of knowledge itself, highlighting the limitations of our understanding and the intrinsic uncertainties that govern the quantum realm. The Heisenberg Uncertainty Principle, one of the most groundbreaking concepts in quantum mechanics, introduces a fundamental limitation to how precisely we can measure certain pairs of properties of a quantum system, such as position and momentum. This principle, articulated by Werner Heisenberg in 1927, challenged the classical notion of determinism, where it was believed that if we knew the position and velocity of an object, we could predict its future state with perfect accuracy. The uncertainty principle, however, tells us that at the quantum level, this is simply not possible. The more precisely one of these properties is measured, the more uncertain the other becomes. This uncertainty is not due to the limitations of our measuring devices, but is an intrinsic property of the quantum world itself. Heisenberg's principle is mathematically expressed as the product of the uncertainties in position, delta x, and momentum, delta p, being greater than or equal to a constant, specifically Planck's constant, he, divided by 4, p. The relationship is represented as delta x c dot delta p gq frac h 4 pi. This equation quantifies the uncertainty in both properties. The constant h is extremely small, reflecting that at the quantum scale, these uncertainties are significant, but not as noticeable at larger, macroscopic scales. The uncertainty principle tells us that particles like electrons cannot have well-defined positions and momenta at the same time. This discovery was revolutionary because it contradicted the classical idea that if we could measure a system's state accurately enough, we could predict its behavior with complete certainty. Instead, the uncertainty principle highlights the inherent limits of our knowledge at the quantum level. The uncertainty principle leads to another concept that has reshaped our understanding of the quantum world: wave-particle duality. In classical physics, particles and waves were thought to be distinct entities. A particle, like a ball, had a definite position and velocity, while a wave, like light, was spread out over space. However, quantum mechanics revealed that particles, such as electrons, exhibit both particle-like and wave-like behavior depending on how they are observed. This behavior is called wave-particle duality. When an electron is not being observed, it behaves like a wave with a spread-out probability of being found in different positions. But when measured, the wave collapses, and the electron behaves as a discrete particle with a specific position. This duality is closely tied to the uncertainty principle. The act of measuring the position of an electron forces it to behave like a particle, but the measurement disturbs the wave, increasing uncertainty in its momentum. Therefore, the uncertainty principle helps explain why particles can behave as both waves and particles. An important consequence of the uncertainty principle is the concept of the observer effect. In classical physics, measurement was assumed to be a passive process. The observer simply records the properties of a system without influencing its behavior. However, in quantum mechanics, the observer effect plays an active role. When we measure a quantum system, such as the position of a particle, the act of measurement collapses the system's wave function, forcing it into a definite state. This act of measurement disturbs the system and introduces uncertainty in the complementary property, such as momentum. The uncertainty principle thus reveals that the process of observation is not neutral but alters the state of the system. This challenges our traditional understanding of observation, where the observer is assumed to be independent of the system being observed. Instead, the observer and the system are intricately linked, and measurement itself is a key factor in shaping the quantum state. The uncertainty principle also has profound philosophical implications. Classical physics operated under the assumption that the universe was deterministic. If we had complete knowledge of a system's current state, we could predict its future behavior with absolute certainty. This worldview, which was rooted in the teachings of Newton and others, suggested that the universe was like a giant clock running in a predictable and orderly fashion. However, the uncertainty principle fundamentally challenges this view. It tells us that, at the quantum level, there is no such thing as absolute certainty. The future behavior of a quantum system is not fully determined by its current state. Instead, quantum systems are governed by probabilities, and the act of measurement plays a crucial role in determining the state of the system. This shift from determinism to probabilism has sparked philosophical debates about the nature of reality and the limits of human knowledge. If the universe is fundamentally uncertain, then what does that say about the nature of the world around us? Can we ever truly know anything with absolute certainty, or is uncertainty a fundamental characteristic of the universe? Another critical aspect of the uncertainty principle is its influence on quantum technologies. While the principle introduces a limitation in our ability to precisely measure certain properties of quantum systems, it also underpins many of the technologies that rely on quantum mechanics. One of the most significant applications is in the field of quantum computing. Unlike classical computers, which process information as binary bits, 0 seconds and 1 second, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to the principles of superposition. The uncertainty principle plays a key role in this ability, as it allows quantum systems to exist in multiple probabilistic states at once, enabling quantum computers to process information much more efficiently than classical computers. Quantum computers have the potential to revolutionize fields such as cryptography, optimization, and artificial intelligence by solving complex problems that are currently intractable for classical machines. The uncertainty principle also plays a vital role in quantum cryptography, which is used to create secure communication channels. In quantum key distribution, for example, any attempt to intercept the quantum key will disturb the quantum system and reveal the presence of an eavesdropper. The uncertainty principle guarantees that the act of measurement will disturb the system, making it impossible for an unauthorized party to obtain the key without being detected. This ability to detect eavesdropping based on the disturbance of the system is one of the key advantages of quantum cryptography. The uncertainty principle thus forms the basis for secure communication in the quantum age, where traditional cryptographic methods are vulnerable to attack by powerful computers. Finally, the uncertainty principle leads to the phenomenon of quantum tunneling, which has practical applications in fields such as semiconductor technology and nuclear fusion. Quantum tunneling occurs when a particle passes through an energy barrier that it classically should not be able to surmount. This effect is a direct consequence of the probabilistic nature of quantum systems and is made possible by the uncertainty principle. The principle allows particles to tunnel through barriers because there is always a degree of uncertainty in the energy and position of a particle. This phenomenon is crucial for the operation of many modern technologies, such as transistors in computers and solar cells, and it plays a central role in nuclear reactions, including those that power the sundae. In conclusion, the Heisenberg Uncertainty Principle is a profound and fundamental aspect of quantum mechanics that has reshaped our understanding of the microscopic world. By revealing the inherent uncertainty in the measurement of certain properties of particles, it challenges the classical notion of determinism and introduces a probabilistic view of the universe. The uncertainty principle is closely related to wave-particle duality, the observer effect, and quantum technologies, all of which have had far-reaching implications for science and technology. Its philosophical implications have sparked debates about the nature of reality, the limits of human knowledge, and the role of the observer in shaping the quantum world. Despite its abstract and counterintuitive nature, the uncertainty principle has become one of the most important and practical concepts in modern science, driving advancements in computing, cryptography, and our understanding of the universe. The Heisenberg Uncertainty Principle is one of the most profound and influential concepts in quantum mechanics. It asserts that there are inherent limitations to how precisely we can measure certain pairs of complementary properties, such as position and momentum, of a particle at the same time. The more precisely we measure one property, the less precisely we can know the other. This idea revolutionized the way we think about the physical world, challenging the deterministic view of classical mechanics and suggesting that the quantum world is governed by probabilities and uncertainties. This principle is not a flaw in our measurement tools, but an intrinsic characteristic of quantum systems, revealing the very nature of reality at the smallest scales. The principle has profound implications for the way we understand the behavior of particles. In classical mechanics, objects were treated as having well-defined positions and velocities, which could be measured simultaneously with high precision. Classical physics was based on the assumption that if we knew the exact state of a system, its position, velocity, and other properties, we could predict its future behavior with complete certainty. This view of the universe as a predictable, clockwork mechanism was central to the success of classical science. However, the Heisenberg Uncertainty Principle showed that at the quantum level, this deterministic view no longer holds. Instead of being able to measure and predict the exact state of a particle, quantum mechanics tells us that the properties of particles like position and momentum are inherently uncertain and can only be described in terms of probabilities. One of the key concepts tied to the uncertainty principle is wave-particle duality. Quantum objects, such as electrons and photons, exhibit both particle-like and wave-like behavior, depending on how they are observed. This duality had been hinted at earlier in the work of scientists like Louis de Broglie and Albert Einstein. But it was Heisenberg's principle that fully clarified the relationship between wave-like and particle-like behavior in quantum systems. When particles like electrons are not being measured, they are described by wave functions, mathematical functions, that describe the probability distribution of a particle's position and momentum. However, when we measure the position of a particle, its wave function collapses to a single location, forcing the particle to behave like a discrete particle. The act of measuring the particle's position thus disturbs its wave function and increases uncertainty in its momentum, as per the uncertainty principle. This interaction between waves and particles is a key aspect of quantum mechanics and is made possible by the uncertainty inherent in the system. The uncertainty principle also introduces the idea of the observer effect in quantum mechanics. In classical physics, measurement was seen as a passive process. The observer simply records the properties of the system without influencing its behavior. However, in quantum mechanics, the act of measurement is not neutral, it actively disturbs the system. When we measure the position of a particle, we collapse its wave function, forcing it into a specific position. This process disturbs the system and makes it impossible to simultaneously know the particle's momentum with perfect precision. The observer effect suggests that the observer is not separate from the system being observed, but is intimately involved in determining the outcome of the experiment. This concept challenges the classical idea of objective reality, where measurements do not influence the system being measured. In the quantum world, the very act of measurement shapes the state of the system. Another consequence of the uncertainty principle is the breakdown of the classical notion of determinism. Classical physics operated under the assumption that the universe was deterministic. Given enough information, we could predict the future state of any system with perfect accuracy. If we knew the position and velocity of a planet, for example, we could predict where it would be at any future point in time. This view was central to the success of classical mechanics. However, quantum mechanics, with its probabilistic nature, tells us that even with complete knowledge of a system's current state, we cannot predict its future state with certainty. The uncertainty principle limits our ability to make such predictions, as the more precisely we know one property of a quantum system, the less we can know about the other. This probabilistic view of the universe marks a dramatic departure from the deterministic worldview of classical physics and forces us to reconsider the nature of causality and prediction. The uncertainty principle also has important philosophical implications. If the universe is governed by uncertainty at its most fundamental level, what does this mean for the nature of reality? Classical physics suggested that the universe is an objective, deterministic system that exists independently of our perception of it. In contrast, the uncertainty principle suggests that reality at the quantum level is inherently probabilistic and that our observations play a critical role in shaping the state of the system. This idea has sparked debates among physicists and philosophers about the role of the observer in determining the nature of reality. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that reality does not exist in a definite state until it is observed. In this view, the observer is not just a passive participant, but an active participant in the creation of reality. Other interpretations, like the many worlds interpretation, propose that all possible outcomes of a quantum measurement occur in parallel, creating separate, non-communicating branches of reality. These differing interpretations highlight the philosophical implications of the uncertainty principle, challenging our understanding of objectivity, observation, and the nature of existence itself. The uncertainty principle has also led to significant advancements in technology. One of the most important applications of quantum mechanics and the uncertainty principle is in the field of quantum computing. Classical computers process information as binary bits, which can either be 0 or 1. Quantum computers, on the other hand, use quantum bits, or qubits, which can exist in multiple states simultaneously due to the principles of superposition and entanglement. The uncertainty principle plays a key role in this ability, as it allows qubits to exist in superposition where they can represent multiple possibilities at once. This capability enables quantum computers to solve certain types of problems far more efficiently than classical computers. Quantum computing has the potential to revolutionize fields such as cryptography, artificial intelligence, and optimization, offering solutions to problems that are currently beyond the reach of classical machines. Similarly, the uncertainty principle has led to the development of quantum cryptography, which uses the principles of quantum mechanics to create secure communication channels. In quantum key distribution, for example, any attempt to intercept or measure the quantum key will disturb the system, alerting the sender and receiver to the presence of an eavesdropper. The uncertainty principle guarantees that the act of measurement will disturb the quantum system, making it impossible for an unauthorized party to obtain the key without being detected. This application of quantum mechanics has the potential to revolutionize secure communication, providing a level of security that is impossible with classical cryptographic methods. In conclusion, the Heisenberg Uncertainty Principle is a key component of quantum mechanics that has transformed our understanding of the physical world. By revealing the limitations of measurement and introducing the idea of inherent uncertainty, it challenges the deterministic worldview of classical physics and forces us to embrace a probabilistic view of nature. The uncertainty principle is closely tied to wave-particle duality, the observer effect, and quantum technologies, all of which have far-reaching implications for both theoretical and applied physics. While the principle may seem abstract and counterintuitive, it has had profound practical applications in fields such as quantum computing and cryptography. As we continue to explore the quantum world, the uncertainty principle remains a fundamental concept that shapes our understanding of reality and the limits of human knowledge.